Good morning, professors. We are Team 2345266 from Diocesan Boys School. Our research topic is on the structure of critical groups of circulant graphs. The inspiration for this project comes from the chip firing game. We came across this while we were studying Problem 3 in IMO 1986, also known as the Pentagon problem. Putting the problem aside, we find the chip firing game, a variant of the problem, very interesting. Here's an example of the chip firing game on the slide. The game starts with an integer number of chips on every vertex of the graph. And to fire a vertex, we remove as many chips as its degree and add a chip on each of its adjacent vertex. For the example on the slide, when the vertex is labeled 3 is picked, it's connected to two vertices. So when it's fired, 2 chips are removed from that vertex and 1 chip is added to the 2 adjacent vertices. It so happens that the configurations that would eventually reach a certain state form a group. Formally speaking, we define a divisor on a graph G to be a function f, where Vg is mapped to integers, with the degree being the sum of all Fv. For a finite graph G, the image of the Laplacian matrix consists of degree 0 divisors under the chip firing setting. And for any graph G, its critical group, Kg, is the torsion part of the co-kernel of the Laplacian, where the Laplacian is the degree matrix minus the adjacency matrix of the graph. Towards our problem, we say a graph is circulant if by labeling vertices 0 to n-1, and by considering a non-empty symbol Sg, which is a subset of integers mod n, then for all xy that belongs in Vg, xy is an edge if and only if y minus x belongs to Sg. A unitary circulant graph with n vertices is a graph where 2 vertices x and y are connected if y minus x and n are co-prime. In this paper, we managed to completely compute the structures of unitary circulant graphs when n is a product of 2 primes or when n is a power of p. Also, we have determined the smallest non-trivial components of circulant graphs with fixed jumps, which are Cn23, Cn13, and Cn123, in terms of the 2 kinds of Chebyshev polynomials, Tn and Un. You may refer to the exact form in our report. We first looked at integral circulant graphs, whose adjacency matrices have integer eigenvalues. In particular, So proved in 2005 that the union of GCD graphs, where the vertices are connected if the difference of their labels and n have a certain GCD, are integral. Therefore, we focus on the graphs where vertices are connected if that particular GCD is 1, which are the UCGs that we have mentioned. Here are 2 examples of unitary circulant graphs, UCG, when n equals 6 and n equals 15. As you can see, such graphs are always connected because they always contain a Hamiltonian cycle, which travels every vertex exactly once. Generally speaking, circulant graphs are Cayley graphs built on cyclic groups, and in our case, Z over NZ. Ducci and J. Liu showed that in 2014 that in particular for our case, such eigenvalues can be computed by adding irreducible characters of Z over NZ, which are nth roots of unity. Such sums are known as the Ramanujan sum. We managed to compute the eigenvalues explicitly, which is lemma 2 as shown. In particular, when n is a product of 2 primes, the eigenvalue and the corresponding multiplicities are as shown. Furthermore, they have proved that the Sylow subgroups of this critical group are related to the eigenvalues of the Laplacian matrix. To be precise, as shown in lemma 4, what they proved is that for any prime r that does not divide n, the arithmetic valuation of the eigenvalues of the Laplacian transfers to the arithmetic valuation of elementary factors. Moreover, in lemma 5, Rushinen also gave an upper bound of the p-adic valuation of each invariant factors. Thus, the critical group is decomposed into the form as shown. To further simplify the expression, we can take out D, the largest common factor of p minus 1 and q minus 1 that is co-prime with p minus 1 divided by d and q minus 1 divided by d, which gives us proposition 2. However, the mentioned tools were unable to help with the case when q is congruent 1 mod p, as the p-adic valuation of q minus 1 may be larger than 1, and hence there may be components in the form of z over p squared z, or higher powers of p. Therefore, one more result is needed to tackle this case, which is lemma 6. The main idea is that by considering LPQ minus P times I, while the rank is preserved, all eigenvalues are subtracted by P, which bounds the p-adic valuation of eigenvalues, the determinant, and hence we have an upper bound on the number of invariant factors that are multiples of P. On the other hand, we can build a lower bound on the number of invariant factors by considering the p-adic valuation of each invariant factor. Hence, with further computation to rearrange the elementary factors, we can completely solve the critical groups of unitary circulant graphs when n equals pq, which is isomorphic to the components as shown. Here are two examples, the explicit structure when n equals 3p and when n equals 5p. The other case of UCG that we have solved is when n is a power of p. When k equals 1, the graph is essentially complete. We can deduce the structure by considering the GCD of minors. As the GCD of 2 by 2 minors is p, all the entries that follow are multiples of p. But since we have a submatrix with determinant p to the power of p minus 2, again, we have bounded entries of the Smith normal form from both directions, which results in proposition 3. To determine the structure of higher powers of P, we return to the co-kernel definition of the Laplacian. By definition, the co-kernel is generated by x1 up to xp to the power of k, which satisfy the equation RQI. The critical group is determined by reducing the p to the power of k equations. In particular, when reducing R11, we consider another integer linear operator m, where L equals p minus 1 times m. Then we can resolve the issue that all coefficients are multiples of p minus 1, and we will have theorem 2. Here are two examples, when n is a power of 2 and when n is a power of 5. Apart from finding the structure of the critical group when G is a UCG, we also attempted to determine that of circulant graphs with fixed jumps. The difference between such graphs is that the symbol SG would be fixed regardless of the size of the graph n, while the symbols of UCGs depended on n. The examples shown here are the cases when the graph has 9 vertices. For example, in C923, for all I from 0 to 8, each vertex labeled I is connected to the vertices I plus or minus 2 and I plus or minus 3 modulo 9. We focused on circulant graphs of jump size up to 3. We first attempted CN23, and from the toppling rule derived from the chip firing rules, it generates a system where all other vertices can be expressed in the linear combination from x1 to x5. Lemma 7 shows this linear combination where all integers larger than 7 can be expressed by these equations. It can be proved by using induction. Using such relations, we can build a relation matrix M23 between the generators and reduce it to the one as shown. On the other hand, making use of the two kinds of Chebyshev polynomials, we were able to express an in terms of integers Sn, Tn, Un, and Vn, real and imaginary parts of the Chebyshev polynomials. Since the components of the critical group is determined by the GCDs of the relation matrix M23, we can express the smallest non-trivial component Dn23 as shown. Furthermore, when n is coprime with 52, that component is simply the GCD of the 4 real and imaginary parts and n. Using a similar method, here are the results for Cn13 and Cn123, in terms of the two kinds of Chebyshev polynomials. We were also able to reduce the required GCD to simpler forms when n is coprime with 20 and 56 respectively. We went to Chebyshev polynomials because we were inspired what Metnick did in, in 2016. So expressing the non-trivial components in terms of real and imaginary parts of Chebyshev polynomials is by far the simplest way we have found. In fact, Metnick claimed that these claims here we stated are true, but we could not prove the cases when n is not coprime with 52, 20, or 56. But with the help of Sage, we were able to verify these claims. Here are the references that we have cited. Thank you very much for listening.